Hello, I'm Sotiris Apostolakis, a fifth-year PhD student from Princeton University. In this video, I'll present the PLDI 2020 paper titled SCAF, a speculation-aware collaborative dependence analysis framework. This joint work with Zian, Susan, and Greg from Princeton, Professor Cabanoni from Northwestern, and my advisor, David August. Compilers transform the code with a series of optimizations. To preserve the semantics of the source code, optimization respect data and control flow dependencies reported by program analysis. The most challenging part of program analysis is memory analysis, which analyzes memory accesses. By relying on statically proven properties by memory analysis, optimizations limit their applicability. Memory analysis is fundamentally limited in theory, since for any fixed analysis algorithm, there is always a counterexample input for which the algorithm is imprecise. Memory analysis is also insufficiently precise in practice, especially for languages like C and C++. But even if analysis was precise enough, still, it would have to conservatively respect all possible inputs, even though there are cases where real dependencies rarely manifest and thus could be ignored. Such cases are, for example, error conditions for malformed inputs. Speculation, on the other hand, overcomes the applicability limitations of memory analysis by enabling optimization of the expected case. Speculation is most prominently used by parallelization transformations, where high-performance gains can compensate for overheads introduced by speculation. To estimate data and control flow dependencies among instructions, speculation typically relies on profile information produced during offline runs of the program. We refer to predictions based on profile information as speculative assertions. Now, the problem is that in state-of-the-art compilers, program analysis is unaware of these speculative assertions. This makes this approach modular, since memory analysis algorithms can be developed independently of speculative techniques, but it also prevents any interaction among them. Therefore, it fails to fully leverage these speculative assertions, leading to either missed optimization opportunities or use of unnecessary and often expensive additional speculation. We characterize this state-of-the-art approach as composition by confluence, since the result of this composition is just a confluence of individual components' results. There is no collaboration. I will now demonstrate the limitations of composition by confluence with a motivating example. Here, we have a part of a simple loop. There's a heavily biased branch that in practice is never taken, but we cannot prove that statically. And instructions I1 and I3 write to A, and instruction I2 reads A. On the right hand, you can see the control flow graph for this part of the loop. Given this code, a client wants to determine whether there is a cross-iteration dependence from instruction I3 to I2. Such a client could be a parallelization transformation that needs to remove all cross-iteration dependencies so that each iteration can execute independently and in parallel. A compiler using memory analysis cannot statically disprove this cross-iteration data flow from I3 to I2, since there is a feasible path where the stored value in instruction I3 flows to I2 in the next iteration. Given that there is a biased branch here, one could attempt to use control speculation and assume that the true path is never taken. However, control speculation cannot assert on its own the absence of the dependence in question, since neither I2 nor I3 are speculatively dead. Therefore, composition by confluence fails to remove this dependence. The problem here is that memory analysis is unaware of the speculative assertion that the branch is never taken, and thus it has to conservatively consider both paths, and the speculative assertion ends up being wasted. The solution is to make memory analysis aware of this speculative assertion. Since control speculation will validate it, memory analysis can treat it as a fact, ignoring the possibility of misspeculation. By doing so, memory analysis can view I1 as executing on every iteration, and thus it can infer that I1 kills the cross-iteration data flow from I3 to I2. So in this example, to maximize the impact of the control speculation assertion, collaboration between memory analysis and control speculation is necessary. One previously explored approach to combine memory analysis with speculation is through monolithic integration. In this approach, memory analysis algorithms are extended with knowledge and interpretation of profile-based speculative information. For a motivating example, one would have to extend the kill flow analysis algorithm to interpret edge profile information. This scheme surely increases the impact of certain speculative assertions. Yet, given the diverse set of existing memory analysis algorithms and speculative techniques, creating monolithic and complex implementations of different combinations does not scale and hinders extensibility and maintainability. Motivated by the deficiencies of prior work, we propose a new approach of integrating speculation with memory analysis, called composition by collaboration. The proposed approach does not sacrifice modularity, can be composed by independently developed components, and enables more collaboration than any prior approach, effectively computing the full impact of speculative assertions. This table summarizes the comparison with prior work. Next, I'll present the design of SCAF, a dependence analysis framework that follows our composition by collaboration approach. Given its design goal of being collaborative and modular, SCAF is based on CAF of prior work. CAF is a modular analysis framework where multiple simple analysis algorithms collaboratively resolve analysis queries. Collaboration in CAF is enabled by the use of premise queries. Premise queries allow a module to ask help from other modules regarding propositions beyond its own logic. SCAF is the speculation-aware extension of CAF. Speculation is integrated into the framework with the introduction of speculation modules. Speculation modules express the effect of speculative transforms by interpreting profile information in terms of dependence analysis. Similarly to memory analysis modules, speculation modules can produce premise queries to request help from others. Modules that produce premise queries are called factored, while the rest are called base modules. Communication among modules in SCAF occurs indirectly through a new coordinating component called the orchestrator. The presence of a coordinating component is necessitated by the potential use of speculation. In traditional memory analysis, once a definite answer is found, it is returned immediately to the client. However, in SCAF, the same analysis result may come with different caveats, depending on which modules were involved, since each speculative assertion has different validation costs. Therefore, even if a definite answer is found, clients may want to explore other options with potentially lower cost. Having a centralized component allows clients to instantiate it with their desired configuration in terms of exploration, without any modification to the modules. Note that with this design, modules are decoupled, can be developed independently, and are agnostic to who produces an incoming query or who assists them. In fact, memory analysis algorithms can leverage speculative information without even realizing it, which is an interesting property of SCAF. Queries and responses are expressed using a query language which is based on CAF's query language. I will only point out a few notable extensions over CAF. Since SCAF utilizes speculation, its analysis results might be predicated on speculative assertions, which need to be validated by clients to preserve soundness. SCAF's language also includes new query parameters. To allow modules to communicate speculative control flow information, SCAF introduces a control flow query parameter in the form of dominance information. Another introduced parameter allows modules and clients to specify the desired result of alias queries and let other modules to bail out early if they cannot produce it. For example, someone may want a masked alias result, but most alias analysis algorithms cannot reason about the masked alias relationship. I'll now revisit our motivating example to show how SCAF works in practice. Same as before, the client here wants to know if there is a cross-duration data flow from I3 to I2. To that end, it creates a modref query that asks if instruction I3 may read or write the memory footprint of I2 in a different iteration, assuming some static control flow information. In the next step, the orchestrator forwards the query to the kill flow analysis module. The kill flow module tries to find a flow killing operation along all feasible paths between I3 in one iteration and I2 in a different iteration, but it fails to do so, and thus it returns a conservative answer back to the orchestrator. Given that the orchestrator received an imprecise answer, it forwards the query to another module, the control speculation module. The control speculation module cannot resolve the query on its own, since none of the two instructions are speculatively dead. However, it knows that the branch is never taken based on profile information. Thus, it encodes this assertion in a speculative dominator tree and adds it in a premise query to ask other modules to resolve this simpler variant of the original query. Then the orchestrator forwards this premise query to the kill flow module. Based on the speculative control flow information in the query, the kill flow module views I2 as being dominated by I1, and thus it can infer this time that the cross-iteration data flow is killed. Note that kill flow is agnostic to whether the control flow information contained in the received query is speculative or not. Next, the orchestrator returns this response to the control speculation module, which can now answer the original query, with the addition of the necessary speculative assertion A that the branch is never taken. At the end, the client learns that there is no cross-iteration data flow from I3 to I2 as long as the branch is never taken. Note that SCAF includes many more memory analysis and speculation modules apart from kill flow and control speculation, but I only included in this example modules relevant to this query. Let's now see some evaluation results for SCAF. The main claim that we want to empirically evaluate is that SCAF reduces the need for memory speculation compared to prior work. Memory speculation is the most commonly used and applicable speculation technique. It just asserts the absence of non-observed during profiling memory dependencies. But memory speculation is also the most expensive to validate speculation technique, and excessive use of it often negates its enabling effect, as often observed in parallelizing compilers. Thus, SCAF aims to increase the impact of cheap-to-validate speculation and remove dependencies that would otherwise lead to use of memory speculation. We evaluate SCAF on the hot loops of 16 C++ benchmarks from the spec CPU suites. And we evaluate SCAF against composition by confluence, which is the best prior approach of integrating speculation into dependence analysis. I described it earlier, but just as a reminder, in composition by confluence, each speculation module is considered in isolation and independently of memory analysis. There's no collaboration whatsoever. This figure presents the dependence coverage by different schemes for all the possible memory dependencies in the hot loops of the 16 evaluated C++ benchmarks. CAF denotes dependencies disproven by memory analysis. Confluence and SCAF bars denote additional dependencies removed by these two schemes. Memory speculation asserts the absence of the remaining dependencies that do not manifest during profiling. And finally, observed depths are dependencies that do manifest during profiling and thus cannot be speculated. SCAF significantly outperforms composition by confluence in terms of removed memory dependencies. There is a 56% geomean improvement. Since both SCAF and confluence use the same inexpensive to validate speculative assertions, these results demonstrate that SCAF maximizes the impact of these cheap speculative assertions by exposing them to all the modules within SCAF. By doing so, the need for expensive to validate memory speculation is dramatically reduced, as can be seen by the 58% geomean reduction in the red bar. To better understand the source of improvement for SCAF, we evaluate which forms of beneficial collaboration exhibited across the hot loops of the 16 evaluated benchmarks. We characterize the collaboration as beneficial if two or more modules collaboratively resolve more queries than in isolation. The results presented in this table strongly corroborate the hypothesis that collaboration between memory analysis and speculation is beneficial. These results also show that there is a beneficial collaboration among speculation modules for most of the benchmarks, a form of collaboration never explored before. Note also that SCAF enables some form of beneficial collaboration for all 16 evaluated benchmarks and for 2/3 of the evaluated loops. This graph shows the cumulative distribution function of the query latency for CAF and SCAF without and with the desired result parameter. SCAF's query latency is reduced by 28% with the introduction of the desired result parameter. Compared to CAF, SCAF increases the domain latency by only 1.6%, despite using more analysis modules. To conclude, SCAF is a modular and collaborative dependence analysis framework that computes the full impact of speculation on memory dependence analysis. Relative to the state of the art, SCAF dramatically reduces the need for expensive to validate memory speculation. Given these results, we believe that SCAF is beneficial for memory analysis sensitive clients and a necessary next step towards robust automatic parallelization. Finally, this paper has gone through the artifact evaluation process and was awarded all the available badges. The artifact is publicly available, can be used to reproduce the evaluation results and corroborate the claims of this paper. Thank you.